Today I will talk about a convergent and orthogonality preserving schemes for approximation the Kohn-Sham orbits. And this is a joint work with Dr. Qiao Wang, Liwei Zhang, and Professor Aihui Zhou. And Aihui Zhou is my colleague. And Dr. Qiao Wang and Liwei are both former PhD students of Professor Aihui Zhou. And now Qiao is working in University of the Beijing Civil Engineering and Architecture. And Liwei Zhang is now working as a postdoctor in University of the British Columbia. I'm guessing that maybe Liwei Zhang is also attending these conferences. And sorry. Yeah, this is the outline of my talk. First, I will briefly introduce some motivation, and then I will introduce an extended gradient flow model for ground state calculation. After that, I will introduce some orthogonality preserving iteration schemes for approximating the Kohn-Sham orbits with the help of the new model we proposed. And then I will use some numerical experiments to validate our theoretical results. And in the end of my talk, I will give some concluding remarks. As we all know that by the Kohn-Sham density functional theorem, the total energy for the four interacting many-body systems can be expressed as this formula. The first term is the kinetic energy, and this term is the attraction energy between the nuclear and the electron. And this term is the Hartree energy, and this is the exchange correlation energy. And the orbitals should satisfy the orthogonal constraints. And the density is the summation of all the orbits. Here, for simplicity, we assume that each orbital is occupied by only one electron. And the VNE is the attraction potential between the nuclear and the electrons. This one is the exchange correlation energy. M is the number of atoms, and N is the total number of electrons. And the ground state can be obtained by solving either the following orthogonal constraint optimization problem or the nonlinear eigenvalue problem. The nonlinearity lies in that the potential depends on law, and the law depends on the unknown's U. So it's a nonlinear operator eigenvalue problem. This equation is also called the Kohn-Sham equation. For this nonlinear eigenvalue problem, people usually use some self-consistent field method to iterations to solve it. That is, we first give some initial input charge density law, and then we can then compute the potential V, and then we solve the linearized eigenvalue problem. After that, we obtain the output charge density, and then we check if check the differences between the output density and the input density. If not converge, we use some density mixing method to get the new input charge density, and then we repeat the loops. Anyway, at the SCF iteration, the central computation in solving Kohn-Sham equation is the repeated of solution of this algebraic eigenvalue problem. So usually this problem is huge dimensional. So there comes two questions. The first one is the convergence of the SCF iteration, and the second one is the solution of the large-scale algebraic eigenvalue problem. For the convergence of SCF iteration, there are some literature, not so many, but there are some literatures about the discussing of it. Here I list some of the works, but limited by the time. I will not go to the details for each of them. Anyway, the performance of the SCF iteration is unpredictable, and the theoretical analysis is very challenging. And for the the solution of the large-scale eigenvalue problems, the existing methods usually need some organization operation. Of course, in the recent years, there are also some work that to avoid the large-scale orthogonalization operations methods are coming. And for the constraint optimization method, there are also some works. In fact, many different kinds of optimization methods are introduced to deal with this problem. For example, the gradient method, the conjugate gradient method, the Newton method, and trust region method, and so on. Anyway, for most of these works, some orthogonalization operation is usually needed. So anyway, just start from both the constraint optimization problem or from the nonlinear eigenvalue problem. Some orthogonalization operation is usually needed to solve to calculate the ground state. And today I will introduce a new model that is an extended gradient flow model. It is a time-dependent problem. It's formally different from the nonlinear eigenvalue problem or the constraint optimization problem. For this new model, we can prove that the flow is orthogonality preserving, and the flow will evolve to the ground state. And based on this new model, we also propose some orthogonality preserving iteration schemes, and for approximation the Kohn-Sham orbits. And we have proved that the approximation converge to some ground state, and under some condition we can prove that there are some convergence rate that is converge linearly. And most of what my talk here is based on the following two references. Now we turn to the introduce the extended gradient flow model. Before introduce our new model, I would like to first introduce some basic notation and the definition. First, we define the inner product matrix for two functional wave vectors like this. So if U is some matrix, then it's just the inner product. And then we define the norm for a functional vectors as the trace of the inner product matrix, like this. And since the orthogonal constraints of the orbits, so we define the Sweep manifold is a manifold like this, that U belongs to H, the Hilbert space, and it satisfies this condition. And then we introduce the distance for two functional vectors like this, the summation of the normal of the normal norm of the differences of two vectors, and then under the corresponding data neighborhood like this. Yeah, since for our energy functional, it satisfies this equation, that is EU equal to EUP. Here, P is any unitary. R is a set of unitary matrix. So this means that that our energy functional is invariant if we do any unitary transformation to the orbits. Therefore, to get rid of the non-uniqueness, we consider our problem in the Grassmann manifold, which is the quotient of the stiff manifold defined like this. And we then introduce the equivalence class and the tangent space on the Grassmann manifold. And similarly, we can also define the distance on the Grassmann manifold like this. The difference is that this is the normal differences distance. This is the distance on the Grassmann manifold, and the corresponding data neighborhood of the equivalent class. This. Once we have these notations and the definitions, we can introduce our problem easily. For our problem, for our energy functional, the gradient on the Hilbert space is like this. Here, H is the Kohn-Sham operator, and the gradient on the stiff manifold is defined like this. Is there another term is added to the normal to the gradient on the Hilbert space, and and we also introduced the extended gradient, whose definition is like this. So this is the key of our new model and also the key of our new algorithm. So different from the gradient on the stiff manifold, we extend its domain from the stiff manifold to the Hilbert space, and we add this one, yeah. And for the simplicity of expressing our algorithm, we introduce an extend gradient operator, AU, like this. AUU is just the gradient GEU. And the hashing of our energy functional on the Grassmann manifold is like this. Then we introduce our extended gradient flow model. That is, this is our new model. That is, we find the U such that it satisfies this equation, and the gradient GE is the extended gradient and of the energy functional. In the following, all the gradient G means the extended gradient energy function. Extended gradient of energy function is, it doesn't means, so here I use the same notation, but this means this one, not this one. Yeah, for this new model, we can prove some good property that it has some good properties. First, we prove that if U0, if the initial orbital is in the stiff manifold, then we can prove the solution of the for all in all time instance it always belongs to the stiff manifold. And besides, we have prove the gradient, the derivative of the energy function with respect to the t is smaller than 0. This means that the flow of the new model is orthogonality preserving, and the corresponding energy functional is strictly non-increasing. And we also prove that the limited inferior of the gradient of the gradient of our energy functional equal to 0. Here we should know. I want to point out that we didn't have any assumption for the energy function. We can for the operator or for the definition of the we didn't have any assumption on the on the energy functional, we can prove this property. So if we do more assumption for the problem, that is you assume that the local minimizer U star is the unique critical point of EU, and you assume that the gradient of the energy functional is continuous in the neighborhood of the local minimizer, and the initial value, initial data U0 is in some neighborhood of the local minimizer. We can prove that with the extent prove that the extended gradient of energy functional evolves to decrease to 0, and the energy functional decay to the minimal energy, and the solution decay to the local minimizer. And if we do more assumption for the energy functional, that is we accept all the former assumptions, we add these assumptions for the energy function, that is the Hessian of the energy functional is positive definited. Then we can obtain that the gradient, both the extended gradient of the energy functional and the area of the energy functional will decay to 0 exponentially. So it means that we do not need to wait for a long time to reach the ground state. We only need to wait maybe a short time, then we can obtain the ground state. And then I tend to introduce some orthogonality preserving iteration schemes based on the new model we proposed. We first consider the finite dimensional discretization of our model. That is, we assume that VNG is a finite dimensional space, and then we can define the corresponding Sweep manifold M and the Grassmann manifold G as before, and then we obtain our discretized gradient flow model, that is finite EU belongs to VNG and such that it satisfies this equation. And we then consider is a time dependent problem. So we consider is a time discretization. We first choose a partition of the time interval like this, and then here we choose the middle point scheme to discrete it. This is the middle point scheme, and then we obtain our middle point scheme for our scheme. That is, we first give some initial data, and we calculate the gradient of the gradient of our energy functional, and to test if the gradient is larger than, is smaller than some given epsilon. If it is not, then we choose a suitable time step, and we solve this equation and obtain a new orbital, and then we calculate the gradient of the energy function. Yeah, the gradient of the energy function, and then we repeat this loop. And for this middle point scheme, we can we also prove that it almost possesses all the good property of the original model. That is, first we prove that if U0 is in the Sweep manifold, then all UN is in the Sweep manifold. Here we didn't do any assumptions. And if we do some assumption to the initial data and to the energy functional, we can obtain some better property, that is that is we can prove the limited of the gradient of that is the extended gradient of energy functional will evolve to 0, and the energy functional will evolve to the local minimizer, local minimum, and the solution will evolve to the local minimizer. And if we do more assumption for the energy functional, that is, we also assume that the Hessian of energy functional is positive definitely, we can then obtain the convergence rate of the approximation. And then we I introduce another scheme that we call it as the interpolation based scheme. It is motivated by the middle point scheme, but it is a little, it is some is how to say. Yeah, let's see the details of the scheme. That is we choose a partition of the time interval, and we consider these schemes that here different from the middle point scheme. This middle point scheme here, the is just the half of un plus theta ut. Here we make use of a ox is a piecewise smooth auxiliary mapping, which satisfy that in the at the times instance Tn it should be equal to un. Yeah, it is just some framework. Is we only give the details of give the exact expression for this auxiliary mapping, but just give some general form. Yeah, and this is our the general framework for our interpolation based scheme. That is, we first give some initial data and calculate the gradient of the energy functional. And test that if it is satisfy our criterion. If not, we then choose a time step Tn, data Tn, and we define the auxiliary mapping ut, and such that it satisfy that it at the start point it should be equal to un, and then we update un by solving this formula, this equation. And for this general framework, we have also proved some good property. That is, we proved that if u0 is belong to the Sweep manifold, then all the un obtained by the algorithm belongs to the Sweep manifold. And if we do some assumption for the sequence, that is, if the sequence obtained by the algorithm satisfy the energy decreasing property, and then we can prove that the limited inferior of the gradient of the extended gradient will be equal to 0. And in further, if we assume that the local minimizer is the unique created point in the neighborhood of the local minimizer, we can prove that the limited of the energy functional will be just the local minimizer, the minimum energy, and the solution will the sequence will converge to the local minimizer. And similar to the middle point scheme, we can also prove that if we do a little more assumption for the energy functional, that is the function of the energy functional is positive definite, we can obtain the convergence rate. like the same as the middle point scheme. Yeah, in this scheme, we didn't give any detailed expression for the auxiliary mapping U, and in fact, we didn't have any restriction for the mapping. We have many different choice for them, and the time step we also didn't give the detail for, but just assume that it should satisfy the energy decreasing property. And now we will introduce some specific choice for the mapping. The first one is that we can choose the mapping like this. Is like this formula is just the linear linear functional. Yeah, it is just linear interpolation by from the like UN and theta UT. And so if for these choices, if we choose alpha n equal to 0, then the auxiliary mapping UT is just UN. This is so we obtain this scheme. This scheme is just an approximation of the Planck-Nixon scheme. It's a little different. Yeah, here is just this is the only differences. It's very similar to this scheme. And if we choose alpha n equal to 1/2, then we can obtain the auxiliary mapping like this. It's just the middle point scheme, which we have introduced before. And in fact, we can also give some other choices. And for the time steps, we assume that it should satisfy the energy decreasing property, but we didn't tell you how to define it and how to find it. Here I show an example that is that can tell us that the indeed exists some time step which is satisfy our assumption. That is, we prove that for the middle point scheme, if the initial guess is if is in the neighborhood of the unit of the local minimizer, and the time step is small enough, then the energy will decreasing like this. So it tell me that our assumption is reasonable. There exists indeed exists some such kind of time step, but of course we cannot say that it is an optimal one. In fact, it is not an optimal because we assume that here it should be small enough. So small enough means that we need a lot of time steps to reach the convergence. And here I use some numerical example to validate our theoretical results. First, this is the Meson test for Meson. This is the charge density. This is the density. This is the mesh, and this is the convergence scale of the energy, and this is the convergence and scale of the gradient. Yeah, and this is another system. Anyway, all this system tell us that our algorithm indeed orthogonality preserving and indeed can obtain the convergent results. I'm sorry, maybe a little. Anyway, now I come to the concluding remarks there. Anyway, we have proposed an extended gradient flow model, and we prove that the new model preserves orthogonality and the flow evolves to the ground state. And we propose some orthogonality preserved schemes, and then we prove the convergence, the local convergence rate of the scheme. Anyway, this work is not so mature, so there are still many topics we need to ask to do further studies. And so, thank you. I'm sorry for